Okay, our numbers are rising, but we're a couple minutes in, so I'm going to go ahead and get started. Welcome to our third and final workshop in the Climate Engine thematic training series. Today's workshop will be accessing drought and vegetation production data for decision support using Climate Engine tools. I'm Tim Asau. I work out of the National Operations Center, where I'm the remote sensing coordinator for the Assessment, Inventory, and Monitoring Program, also known as AIM. I coordinate efforts to integrate remote sensing into the AIM program, and we do that in a number of ways, including research collaborations, one of which is with Climate Engine. Before we get into the training, I just want to mention a few points about how this collaboration began. And if you've been on other trainings, I'm trying to make this like a little bit different each time. So hopefully if you've been here all 3 times, you're not too bored. The evolution of this collaboration goes back over 10 years. It started with Sarah Peterson, who began this work when she was with the BLM Nevada State Office. Now she's with the USGS. Alden Shellcross then championed this work during his time in Montana, and he continues to be connected through a number of initiatives. Then several BLM headquarters programs invested, not only AIM, but also the range and aquatics programs. There's been a number of people involved with that, including Paula Cotillo, Emily Kajirgis, Justin Shirley, Jessica Phillips, and Scott Miller. So why the collaboration? Well, monitoring is a very common theme among programs within this agency, and anything we can do to further that is important. Within AIM, integration with remote sensing is one of the 6 principles of that program. And to achieve that, we have 3 AIM remote sensing priorities. These are scientific relevance. We want to use the best available science to make decisions, and that's something that's always changing. So we want to stay on top of that. We want to communicate data and workflows for decision makers to lower the barriers and increase access for folks within our agency. And finally, we want to foster collaboration. This allows us to leverage diverse scientific expertise and meet those first 2 priorities. So why do I think this collaboration is significant? We've all heard the phrase data to decisions. It's a great phrase, but there are a lot of challenges associated with that. We have more data than ever before, but it can be very overwhelming with respect to understanding how to use it, to interpret it, and to access it. So getting it in a digestible form for our managers to make these decisions, with it is a big lift. We all have limited bandwidth these days, and so these are a couple reasons why I think the collaboration is significant as Climate Engine is helping us to achieve these priorities within AIM, as well as some of these other programs. So how are we using these tools? First, the summary reports. We're going to hear about those today. The summary reports for a given area of interest are loaded with all kinds of information. Some of you have a lot of experience with that already. Also with the Climate Engine app, there are a ton of analysis options. And I hope you take away a lot of things from the next 2 hours. But as we've been talking about, and we talked about last week, in my opinion, this app is like exploratory data analysis on steroids. It allows you to do all kinds of things, and it's a great first stop when you have a question and you're looking at a given area to see how you might address that question. So we'll see plenty of examples from those today. But finally, we also have access to this data through the Climate Engine API. And although we won't discuss it, we've got a number of things in development for our power users, whether that's Google Earth Engine using JavaScript, Google Earth Engine using the Python API, access via R, and even an Arc Pro toolbox that will allow users to access their API and bring some of this cloud-based remote sensing data into Pro. I won't go into all those details, but these data sets are massive, and it's not tenable to store them locally, certainly for large areas. Climate Engine's data catalog is enormous, and that's why remote sensing operates in a cloud-based system these days. And I can't stress enough that it's not just a few of these derived remote sensing products, although those are, such as the fractional veg cover, are massive data sets in their own right, but also a ton of various forms of satellite data along with climate data that we have access to through this route, this avenue. So in short, we're working on additional capacity for how we can extend custom analysis for that population of users. But to step back, today is going to be to focus on reports and the application. You won't need to know how to code to generate any of the information that will be shared today. And then furthermore, we're going to hear from someone in the Montana State Office as to how they've been using this information to address management needs. Today's training is a deeper dive into drought and herbaceous plant productivity. We had a broad foundational training back in June of 25, and then we've had multiple thematic trainings recently, riparian and wetland 3 weeks ago, and then upland vegetation last week. So the slides from today's meeting will be shared as well as the recording. And don't fret if you're trying to work alongside. I may actually encourage you to observe. The folks at Climate Engine do a great job of embedding links in all their slides that will take you to dynamic examples that you can explore in deeper depth later. And this is because it's a cloud-based product that's available to anyone and everyone with an internet connection. Okay, so with that, enough about me. I'm going to pass it over to Kristen O'Shea, and we'll get going. Kristen, take it away.
Awesome. Thanks for that excellent introduction, Tim. So we're going to hop right in. Tim gave a really good ramp up of what we're going to talk about. We're going to really dive into different data sets that we can use to really understand current conditions, trends, how drought's changing, how productivity is responding. So as Tim said, this is the third training of our trio of thematic trainings. To give you a little overview of what to expect, we're going to have a quick background and overview of Climate Engine and our partnership with the BLM. And then we're going to really dive into drought, the data sets, how to summarize them and utilize them in these different tools, going over our drought reports, and then we're going to do a demo specifically on drought. Then we'll change pace to a vegetation production section where we'll do pretty much the same outline. We have a BLM practitioner highlight, and then we'll provide resources and wrap it up for the day. And so you have two instructors for this workshop. My name is Kristen O'Shea. I'm a geospatial data scientist on the Climate Engine team at the Desert Research Institute. I work a lot with our partners to co-develop workflows and really understand their needs for data, how we summarize it, how we visualize it, and making that really accessible to everybody. And I lead multiple of our projects with Dakotas. And I'll let Eric introduce himself.
Hi, everyone. Happy to be here. My name is Eric Jensen. I'm a research scientist at Desert Research Institute and work closely with Kristen on Climate Engine. I lead our work with the Bureau of Land Management and with the National Park Service, and so co-lead the work with the National Park Service, and so have a real focus on resource management and conservation applications of remote sensing data. And so, yeah, I'm excited to be here with all of you today and to hopefully share some tools that are useful for all of you.
Awesome. So before we hop into our background and overview, I have a little icebreaker that I want everybody to participate in. It's super easy. So the top of your team screen, you're going to see React, where it provides different options for you to react. And so I want everybody that has created a Climate Engine data product before to give me a heart. It's going to look something like that. Awesome. That's great to see. So we already have some people here that are familiar with Climate Engine. Let's now have everybody that maybe they haven't created a product, but they've used a product that has been created through Climate Engine tools. Can you give me a clap emoji if that's you? Awesome. And then lastly, if you've never used Climate Engine before and you're completely brand new, can you give me a thumbs up? Awesome. Okay, we have the perfect mix. It's really great. We have a wide variety of people here today, but we have content that hopefully is going to speak to everybody, get you excited. That said, feel free to use the chat. We have multiple speakers and Tim that are going to be looking at the chat and answering questions as we go. So feel free to just hop right in no matter what level you are, because there's other people that are at the same level as you. And let's hop in. Okay, so a little bit more background on Climate Engine. So it began back in 2014 with a research grant from Google Earth Engine Faculty Award. And ever since then, it's really been supported through different agreements, but most specifically, the BLM and Dakotas. And Climate Engine really came about when scientists realized it's a lot of work to pull these vast amount of data sets, like Tim said, down and process them locally. So why not bring those data sets to the cloud and let the cloud do all of that heavy lifting? So Climate Engine really focuses on providing tools that make that cloud-based processing of these extremely large data sets more accessible, easier to use. So at the end, you just have a product that you're able to put in a report, summarize, and move forward. And we do this by integrating the best available data in a common platform for both summary and analysis and visualization. And so a little more on the Climate Engine BLM partnership. Again, it was initiated back in 2015 through multiple agreements, and it's really grown as Climate Engine has grown to respond to the needs of different BLM users. Currently, we work a lot with the NOC and different program support from AIM Aquatics Range and the Nevada State Office. And we work together to really prioritize what BLM users need most. We really focus on developing and maintaining these tools, integrating decision-ready data sets. We have over 100, which can be really intimidating, but we want to make sure we're continuing to respond and grow to what data sets are needed for decision-making. We're working to support integrations with Climate Engine tools with other software systems and processes. And as today, we're providing these trainings to support staff, and then also where needed, conducting different research and meeting, supporting operational needs. And so in this effort of research to operations, there have been different tools that have been developed out to respond to needs. And one of those has been the need to assess drought severity. And this can be found through an instruction memorandum that points to Climate Engine's web application and reports to be able to access different climate and weather variables and summarize them over time for specific areas. And so we work to make these tools as easy as possible to access and visualize the data. And I wanted to highlight some examples of how people currently in the BLM are using Climate Engine in different reports. So as I was looking through the reports for the Climate Engine web app, I'm seeing a lot of people using it for different annual time series, whether they're looking if something was a dry year or a wet year, or how temperature is changing over time, as you can see in the top images here. I've also seen a lot of uses of plotting things like precipitation with NDVI, which can be a measure of vegetation productivity, to look how things like precipitation are impacting vegetation over time. Through the Climate Engine reports, I'm seeing people using it to determine what % of the area in certain allotments or custom areas are in drought categories and how that changes over time. To pull summaries of annual evaporative demand values and trend, and similar with precipitation, as we can see in the middle here from the site characterization reports. People are pulling vegetation production current conditions and trends, and they're also pulling vegetation production time series. So let's hop right into drought monitoring with Climate Engine. First, I wanted to cover some different data sets that are really important when considering how to characterize drought. Drought can be defined on so many different levels. There could be meteorological drought, hydrological drought, vegetative drought. And so there's a lot of data sets that are available to you to understand what's going on. The first one I wanted to cover was the US Drought Monitor. This is going to be released every Thursday, and it shows parts of the US that are in drought. So all of you might be familiar with these different categories that go from a normally dry to exceptional drought. What this is going to do, it's going to blend physical indicators with expert insight, condition observations, and reports of drought impacts. So you can pull things like precipitation data and other variables that we'll go over, but also things like stream gauge data and how reservoirs are fluctuating. And then also what impacts are being seen on the ground. And they're going to combine all of those together. This data set's going to both depict short and long-term drought in certain areas. As you can see, S's and L's on this image. But one of the limitations is the coarseness and backbox calculation. So I couldn't pull data and come up with the exact same drought monitor as somebody else, which can be a challenge. Next is a data set from UC Merced. It's GridMet. This data set's going to blend high resolution PRISM data, spatial data from PRISM, with high temporal resolution data from NLDAS to give you a product that's a 4-kilometer spatial resolution and available at a daily temporal resolution. And this data set is really well documented and used for a lot of different applications because it is validated using extensive network of weather stations. And it's going to provide you a wide range of data variables from the temperature, precipitation, evapotranspiration to different wind and vapor pressure variables, also drought calculations and fire indicators. Once you have different inputs, such as precipitation or evapotranspiration, you can start calculating a different type of indicator than the USDM, and that's a drought indice. So I have 4 outlined here. We see a standardized precipitation index, which on the right, we have a nice little image that shows rain. So that's, I like to think about that as the moisture coming into the system. We have that precipitation, and that's the only thing you're considering there. Then we have the evaporative drought demand index. That's going to show moisture leaving the system. So we're not considering how much is coming in. We're just seeing the demand for that in the atmosphere. Then we have the standardized precipitation evapotranspiration index, which is going to consider both the in and out of moisture, and then the PDSI, which is going to do the same. Now, I want to note the first 3 can be calculated for any time period. As we'll see in some other examples, there can be standard times, or you can do a custom calculation in Climate Engine. But the Palmer Drought Severity Index is going to be around that 9-month time frame. And so what these indices start to do is understand how conditions of precipitation or evapotranspiration are acting during a specific time. So say I want to know SPI for the last 30 days. What I would do is pull precipitation values for those 30 days, and then also for 30 days during a climatology time period. So I might pick 2025 all the way back to 1995. And what I'm going to do is take those 31 values or 30 values, and I'm going to fit them to a distribution that looks something like you see on the screen here. And then I'm going to take the last 30 days and figure out where they fall along that distribution. And so we can see these percentiles mapped to this distribution. So if it was exceptionally, this is Eddie, so it's a little backwards. But if I was in this exceptional category, that means that there would be a high number of precipitation values closer to the mean, and it would be extremely rare to get the last 30 days value. And so we can see here, these different percentiles are then mapped to z-scores that are how far away from normal is this precipitation value. And so for SPI and SPEI, when you are greater than 2 away, that's an exceptionally wet. And then we're going to see the inverse for the eddy values. And you can work your way through and see all the way at the bottom when your values are less than -2, that's going to be exceptional drought. So this allows us to start thinking about these different meteorological inputs and how rare they are relative to past experiences in understanding drought. GridMet Drought does all of these calculations for you. It's derived every 5 days, and the standardization is done using a specific, it's using a non-parametric, so that's telling you the shape of the distribution that it's matching all of these values to. It's also going to use a time period of 1981 to 2016, and it includes all of these different SPI, and eddy values at different time periods. And so you can utilize these different indices to create other indices, such as the short and long-term drought, which I have images here, that can identify certain types of drought. Short-term might identify more vegetative drought, something that's going to react to a shorter time period where we have less moisture in the system. And then long-term drought maybe could indicate more hydrological drought. So the question that comes from this is, which one do I pick? The USDM or the standard indices? They both say that they're identifying drought and what categories, but they don't always match. So the standard indices, you can really think of them as these objective formula-based climate signals. They're fast to respond to moisture coming in and out of the system. You can reproduce them with multiple different data sets, and it's really good for setting thresholds or looking for trends. The U.S. Drought Monitor, on the other hand, it's going to integrate many indices. It's going to include expert judgment, and it incorporates impact reports, but it can't be reproduced, and it's impact focused. And so I pulled the long-term drought and the drought classification for the same time period here. And you can see that while there's things that match, the USDM is going to be a little more broad, where we're going to have more detailed scale to the long-term drought blend. It's a little bit higher resolution. But when they disagree, they can just be describing different parts of the drought system. And so you can think of, well, maybe the impacts I'm seeing in the U.S. Drought Monitor are from a previous time or not captured within these standard indices. So you can use them in tandem together to better understand drought. And so in understanding how to both access and pull drought data from Climate Engine, I wanted to cover a tool available in our app that is a little bit less used right now, but we really want to let people know is available to them, and that's the Climate Engine feature summaries. So what our team did was go through for all of the state offices, field offices, district offices, and allotments, went through and did the zonal statistics on every single boundary for different variables to allow you to have this chloroplast-like map where you can see how different areas in multiple allotments at once are looking like maybe in drought, or is precipitation less than average. And that's what I have an example of here. You can see it's a percent of average conditions for the last 30 days, summarized to each allotment. And the areas in dark brown are going to be less precipitation, and the areas compared to average. And then the darkest green can be up to 800% of average, which we saw some rains there. These are also available for different drought indicators. So we have the long-term drought blend here. And so we can see some of the areas that are currently in drought down in Arizona and New Mexico. And so I wanted to show everyone how we can jump in and create these. So if you head to app.climateengine.org, it's going to bring you up to our browser-based tool. So as you saw in our Climate Engine Basics, you don't need to download anything to use the Climate Engine web app. It's going to pop up here in your browser once you sign in. Again, it's free to get a account. We have those two different functions, making maps and graphs. And then under here, right at the top of Make Map, it says Visualization Layer. So what you can actually do is switch that to feature summaries. We have U.S. regions for the Bureau of Land Management. And then all of those different levels that I was telling you guys about, we'll stick with grazing allotments. And then it works very similar to Climate Engine. We have both climate and remote sensing summaries. We'll stay with climate for now. You're going to see a much more pared down set of data sets than you do for the raster layers, but we have both GridMet and GridMet drought summaries. If we stay here, we see we have different temperature, precipitation, evapotranspiration, and wind speed variables. So if we just keep it like this, let's remake the last 30 days, or we'll do percent of average conditions for the last 30 days. And then you just click compute map like you do for the rasters. And you can zoom in to a specific area, see how the values, we click on it, it's going to actually tell you. So it's 63% of average for that allotment. And then we're also going to have links to the different reports for that allotment. So I'm going to show another example. I'm going to do GridMet drought. We'll go the long-term drought blend. And then I'm going to pick a time period that could be relevant for productivity. So if I'm wondering, okay, what time period could drought be impactful for productivity? We can look at the last March through May. I'm going to zoom back out. And so it's going to show us up here. That was March. This was March through May of last year. So this says 2026. I'll have to fix that. It's definitely 2025 because we haven't had March yet of 2026. But we can kind of inspect and see these areas that are more in long-term drought. I'm going to come up to this example here. This looks like, and we have the little question mark here, extreme drought. I'm going to click on this allotment. And it's going to tell us, yeah, it falls within the -2 value. I'm going to go check out the drought report. I want to know more about this allotment. So it's going to take you right to that report for that allotment. So this is really great if you want to go out and you're like, I want to find more areas that maybe I want to go investigate more. I want to focus my my field visits on, but we see that it's most recent. So I'm going to hop back to that March time period. And we can see, yeah, that long-term drought, it was what percent? 90% was in that exceptional drought category. We also see there that this trend, it's actually been in most of the allotment in exceptional drought over time. So we have the percent of this allotment, and we see almost all of it is in that exceptional drought there. And that's a trend that is more recent. And so I'm going to leave this, but you can then go look at things like productivity, vegetation covers, and trend in that area. So Eric will pick that up when we head to the production part of this. Next. Oh, and here, for if you come back, we have a step-by-step article, report, and video tutorial, all stepping you through what each piece of this drought report looks like, how you can interpret it, and utilize it for understanding drought conditions. And with that, I'm going to hand it to Tim for any questions. Feel free to raise your hand, and yeah, we'll dive in.
Hey, thanks for kicking us off there, Kristen. I was just furiously typing a response, but I think I might read it to the crowd instead. Great question comes from Charlotte. Are you able to generate a report based on a polygon? I tried to generate a vegetation report from last week on a BLM partial that's not within an allotment, but I wasn't able to access the report. You're not able, Eric and Kristen can correct me if I'm wrong here, You're not able to generate a report from the feature summaries per se, but yes, you can create a custom drought report for your AOI. Kristen is demonstrating this right now. So you can go in, there's some pre-selected areas, Huck 10, Huck 12, couple of other areas as well. You can also upload your own shapefile or just draw a polygon on the map. These are a little different than the pre-selected reports that are generated immediately. In this case, you'll get an email, you put in a little bit of information, and you'll get an email back within, usually it's about 5 minutes at the most. So I hope that answered your question, Charlotte. But yeah, really good question.
Awesome. Yeah,
sorry, Kristen,
go ahead.
Go ahead.
I was just going to say, I just kicked it off. So as Tim said, it'll both send the report to your email, but if you wait also that 5 minutes, a little link to download will come up. And it's just the same as the pre-calculated. You can get the underlying data through a CSV, the PNGs for that.
Thank you very much, Kristen. Yes, Charlotte. Maybe that may be a little bit of a subjective question, but I think they are just as pretty as the main reports. You also have an option in there where, and I know this is quite common in some areas of the West. If your AOI, if your shapefile includes some areas that are not just BLM land, there's a little option in the custom reports where you can check a box and it will only include statistics for the BLM land. That said, be careful when you interpret that, because depending on the underlying data set, if it's grid met data that's 4 kilometer, that's pretty coarse. If you're looking at the site characterization reports, that's 30-meter data, it's probably much more appropriate for something like that. Yeah, great questions. Any other questions before we go back to Kristen? And feel free to keep them coming in the chat. This is a nice, efficient way for Q&A.
Perfect. I will
Kristen.
just note that we're not covering it, but you can also request reports through our API. So if you have multiple, say 20 Huck 10s that you want drought reports for, hopefully we'll have future workshops on how to do that. But if you want to dive in yourself at docs.climateengine under reports, you can see how to do that. And we have some demos through our support site. Just want to throw that out there. But yeah, let's hop right back in with our first demo. So this demo is going to be mapping the 2017 Northern Plains flash drought. I really wanted to focus, there's a lot of BLM land that fell within this drought, and there were some fires that came from it. And I want to focus on how we can pull multiple different data sets and variables to tell a story about how drought is progressing. So a little bit of background, and we have a picture there from drought.gov showing just how all of these variables came together to really affect things like crops, rangeland production within this area. So really early in 2017, this area of Montana and the Dakotas were looking like normal conditions for the growing season. But as you can see from this figure from a NOAA report, things changed a little bit over time. There was increasing temperatures coupled with less than average precipitation. There were strong winds, and then also really low soil moisture. And all of these things came together to tell the story of this flash drought that led to a lot of impacts. And so we're going to walk through recreating a lot of the figures, and then maybe where you could take it a step further to explore different impacts of interest to you. So the first thing we're going to do is create annual summary time series. So the links were a little too long, but I will link the shapefile here. It's just a simplified Montana, North Dakota, South Dakota shapefile. But I did take screenshots so you can recreate all of the inputs. So what we're going to do is head to the time series. We're going to pull precipitation and temperature over time for just a specific time period during the year, and give us an annual time series for that. So I'm going to hop right back into the Climate Engine web application. A good practice is to click reset. If you make too many back-to-back map requests, sometimes things can get a little laggy. So I like to, after every 5 requests, just start fresh. And we're going to head to our Make Graph tab. Now, the first thing we're going to do is pick the type of time series calculation we want to do. And so there's the native time series, which would give us every single precipitation value. But for a daily data set like GridMet, that's going to be a lot, and we're not going to be able to see these trends. So we're actually going to choose summary time series. The second thing we're going to do is pick our polygon of interest. And so we can draw a point, draw a polygon on the map with all of these things, but we're going to really focus is a custom polygon from a shapefile. So once we select it, it's going to prompt us to upload our files. I'm going to have a zip file here of my simplified. And the reason I simplified it was I still was able to retain the outline, but it was a lot of vertices from the original shapefile. And so that really, I wasn't getting as long of a time series because it was really complex when I was processing it. So I'm still getting the same output, but just with many less vertices, and it runs much quicker. And so I'm going to pick, there's only one shapefile here, but if you had multiple, you could pick them from that dropdown. And we're going to stay with the climate and hydrology type, GridMet and precipitation. Our statistic over the region is we're going to take a mean, and then statistic over the day range is going to be a total. So we're going to do about a 3-month total. And I'm going to use a custom range. And so this range is going to match one of the figures. And so we're going to go May 1st through July 31st. And then we're going to just go right up to 2017. So once we fill this all out, it's going to calculate. This calculated pretty fast. Again, I simplified the polygon because I was running into some errors. So that's something you can think of. And if you're having any trouble running this type of calculation, sometimes it can be the scale of the data set coming in. So we're doing a 4-kilometer data set, which is much easier. But if we had a high resolution 30-meter, it would probably get a timeout. So those are some of the things that you can play with to be able to return this vast amount of data. And so here we have our precipitation. And what this is actually going to show us is 2017 was an exceptionally dry year. And for that last time period, it was one of the driest years on record. And so if we wanted to utilize this image, we could download it as a PNG or a CSV. And then we also have all of the data here that we could look at. So if we scroll down beyond all the vertices that are still even there, we are given date and precipitation. So these are going to be that total over that 3-month time span. And then all we have to do to look at temperature, I'm going to pick mean temperature, is change it. We notice that our statistic over day range changed to mean. That's because we don't want the total temperature, but we want to average over that time. And it's going to be processing. Awesome. So then we see the figure here. I don't think I said this for the last one, but for the new people newer to Climate Engine, you can see there's red and blue. That's really a distinction of below and above average for this time period. So we take all of the data that's returned, we calculate the average, and then we color it based on those differences. And so here we can see 2017, while not the warmest time period for that year, it is quite a bit above. So we can start pulling apart why we saw this flash drought. We had much lower than average precipitation and greater than average temperature. But that's not the only way that we can start digging in and understanding these different data sets. and how they can be utilized to contextualize drought. So the next thing we can do is we can look at maps and how maps change over time. The really nice thing in Climate Engine, you can make maps quite quickly. And so here I've recreated the USDM maps from this report using Climate Engine. And we can see from April and May, we see most of this area as normal conditions with a little abnormal to moderate drought. However, in June and July, the drought monitor all of a sudden is showing this extreme and exceptional drought that then persists through September. And just to note here, we're taking the monthly maximum USDM value because USDM comes out once a week. You're going to have 4 images within that month time frame on most months to pull from. And so let's hop back into Climate Engine and make some of these maps. I'm just going to reset. I could say, don't show this window again. Awesome. So we're under the Make Map tab. I'm going to move down to USDM, which is under the North America CONUS section of Climate and Hydrology. There's only one data set here. My calculation, I want to take the maximum values over this time period. And I'm going to choose a custom date range. So we're going to start off with that April time period. So this is going to give you a lot more flexibility when you're thinking about the reports are a great starting place, but then if you want to summarize over subsections, Climate Engine gives you the ability to do that. And then even further, if we go to our map overlays, we can go down to the US states just to provide some context in what we're seeing. And so we have our output here of what USDM looks like in that early April. Next, we can move into, we'll skip a couple months, but I have links for all of them for people who want to dig in further. Let's say we wanted to look at July, we would just say click compute map. And it's really this rapid processing that's going to allow us to then visualize and see the differences between these time periods. And sometimes the tilers are a little slow, but they'll come in. And so say we're interested in downloading this data, Climate Engine has a tab download where you would go to the select region. We'd pick a rectangular region. I suggest turning the map overlays off because they get in the way a little bit, but I can just drag this up to the area I'm interested in, make a box. Now, this is quite a big area. There are limitations on how big of a raster you can download from Climate Engine, but it's a little coarser, so I'm going to try. I can name the file whatever I want. So I'm going to do USDM July 2017. It allows you to change the native resolution. You can coarsen it, but then you can say download computed map data. It's going to process that request and it's going to give you a link that automatically downloads it. If it times out or if there's nothing in the request, that means it's too big of an area and you would have to use our API. I did check this one earlier, but for the sake of time, it did download. And you can then open it in ARC or QGIS. Yeah, so that's kind of accessing and mapping USDM over time. Next, we're going to hop in to another way we can look at how drought progressed. So you can create monthly precipitation percentiles. So here we looked at these different month time periods and then compared them to the same time periods in 1979 through 2016. So right leading up to that. And so we can see the fall before this flash drought is actually exceptionally wet in some of the highest percentiles over Montana and Northwest Dakota. And then in April of the year of the drought, we see things starting to change a little bit. But then the jump from April to May is pretty stark. So in April, we have about average to more than average precipitation. But then when we get to May, we're seeing the lowest percentile. That's some of the lowest precipitation throughout that time period. And we just see that persist through the next 4 months. So again, just hopping over to Climate Engine, I'm going to turn off my download. I am then going to head back to GridMet, so you can play around with Prism or other data sets. We'll keep with precipitation. And we're just going to update our calculation to percentile and distribution of past observations. And let's look at what that July looks like. We'll have to update this default year range. And again, I'm going to throw on the overlays since we're not going to download anything. We see that lack of precipitation relative to the time period that we're looking at. So it matches a lot of what we saw in our time period or our time series, much lower than average precipitation. If we hop, I know I'm going a little bit backwards, but if we hop back to that fall before, we can start investigating what that looked like and how maybe that's impacting vegetation or what we're seeing on the ground in those areas. And again, we're just seeing that exceptionally high precipitation relative. Awesome, so that will fill in, but for sake of time, I want to keep moving. There's a lot of cool variables you can start looking at. So when we look at monthly temperature percentile, we can see that that fall before was higher than average temperature. And then in April, it was pretty, consistent. But then we start moving deeper into the season. In July, we see some of the hottest temperatures over that time period. And then in August, it becoming more normal again in most areas within it. So if we were to do that, all we would have to do, again, is hop. I'm going to pull that max temperature over my months and make a lot of requests. So I'm making a lot of back-to-back requests. But that is one of the power of Climate Engine is it is optimized to work with these very large gridded data sets really quickly. And then you could do the same thing. For the sake of time, I have the links here for all of them, but also looking at not just percentile distributions, but you can look at anomalies. So what we can see here is there was actually in June, July, and August, a big drop in evapotranspiration. And this was because of that lack of precipitation and lack of soil moisture. And this also is a great way to show how that flash drought progressed and how it's impacting areas. And then lastly, I kind of wanted to leave it to all of you guys on some ideas about how you can do additional drought-related exploration using Climate Engine. So I have 2 examples here. The one on the left is actually another data set that we have available in Climate Engine called VegDry. It takes vegetation anomalies and combines it with drought indicators to give you an idea of vegetation condition. And so we can see during this time period in July, there was a lot of extreme and severe drought for vegetation. And on the right, there were a lot of fires that summer, and one of them that did touch BLM land was the Bridge Coulee fire. And not that this was the only driver, but the conditions definitely were so that they were ready for, or it contributed. So I pulled the 14-day eddy, which again looks at evaporative demand right before that fire. And you can see that it was showing extreme drought. And we have the fire perimeters within Climate Engine, so we could do different summaries over those perimeters and whatnot. But with that, I will hand it to Tim to field any questions on this demo or anything we've covered with drought so far.
Hey, thanks a lot, Kristen. I really appreciate that. There's a lot of great information. Any questions before this concludes the drought portion of today's presentation. So before we switch gears and go to vegetation productivity, does anyone have any pressing questions they would like to throw out there? And while you're thinking about that, I might offer a thought, and that is, if you're someone who thinks a lot about climate indices, about precipitation, about drought indices, awesome, like do your thing. If you don't spend a lot of time doing that, I fully recognize that this can be very overwhelming. When you go into the Climate Engine app and you select climate and hydrology from the drop-down list, there's a huge list of data sets that are populated under that. And sort of two thoughts for that. One is maybe think about just going to the summary drought reports first as a first cut. And then second, if there's something that really catches your eye, Kristen has had a lot of great slides, some really great slides that show like what's in the drop-down list and all of her links. If you go into those, once you have an account, if you don't already, once you have an account, you can open that up and get a sense for what data set she was using, and then scroll over to your area to get a better sense of that. And then finally, in the Climate Engine app, when you select a given data set, there's that little yellow question mark over there. And if you click on that, yeah, so exactly, this is Kristen's dynamic slide just popped up. That was fantastic. This is the data set that she's using. You just go ahead and click on that question mark. It's going to take you to an information page about that. Again, a lot of information. More information's generally always better, but sometimes I realize it could be a lot. So just keep that in mind going forward. But yeah, when in doubt, start small. And yeah, just my observation. Okay, it does not look like we have any questions from the crowd. So with that, thank you, Kristen. And I'm going to turn it over to Eric Jensen to lead us into the vegetation production monitoring portion of the agenda. Eric, take it away.
Yeah, fantastic. Thank you, Tim. And yeah, really, I think that Kristen's presentation on drought sets up this this portion of the session quite well. We won't leave drought entirely behind. We'll be able to actually bring in drought into some of the ways that we're looking at the response of vegetation to precipitation within water years. So yeah, with that, we're going to jump into the production data. Just touching on one other point that Tim mentioned, you know, there are a lot of data sets in Climate Engine. Kristen said, you know, we recognize that can be overwhelming. There's a reason why here we focus on a handful of data sets. You know, there's a lot of interest in using Climate Engine to compare between different data sets. And so that's why we provide so many data sets. But for your purposes, for the most part, you can use, you know, a handful of data sets. And I think across these 3 sessions, we've probably touched something like maybe, I don't know, 5 to 8 data sets. Like, so you can ignore quite a few different data sets and make really good use of just a handful. And one of those is the rangeland analysis platform. If you attended our upland ecosystem session last week, you saw us present quite a bit on the RAP, and we focused entirely on the vegetation cover data. Here, we're going to be using the RAP production data. The production data, just before I dive into some more information about the production data, it's important to have some understanding of the cover data. The cover data actually, initially the RAP team hadn't even planned to make the cover data available, and it was meant to just be an input into the production model. Turned out people really wanted the production data and you could do a lot with it. But all to say, you know, as you're thinking about the production data here, you know, anything that you understand about the RAP cover data, you can know, well, oh, those are the vegetation types. Those are the vegetation data that are being used as an input into the production models. Yeah, I should also say this data set's produced by USDA ARS, fantastic data partners, and we have more information on our support site. So with the RAP production data, we have two vegetation types, perennial herbaceous and annual herbaceous. Perennial herbaceous is going to be more related to, perennial bunch grasses, rhizomatous grasses, deep-rooted forbs. When we're talking about annual herbaceous across a lot of the western U.S., it'll be noxious grasses and forbs as well to some extent, and in some cases perhaps novel annual systems. But in a lot of places, this is going to relate to cheatgrass, medusa head, tall tumble mustard, plants like that. The RAP production data are produced in units of pounds per acre of above ground biomass. So you can interpret them in the same way you would interpret clipped plots from the field. The data are provided two ways, as annual summaries, so annual maps, and as 16-day maps. So these two kind of views help you to, with the annual data, look at patterns over longer periods of time. Where with the 16-day data, you get kind of a continuous record where you can look at changes in timing of production. You can look at, seasonal changes in timing. You can get kind of a finer picture. The RAP production data are produced at a 30-meter resolution. So each pixel represents roughly the size of the infield of a baseball diamond. Since this is the production session, I want to go just a little bit deeper into how the production data are produced. So this is the RAP production data are produced off of a process-based model, which means the model is trying to represent the process of plant biomass production. It's a 50-year-old model in ecology. It's referred to as the light use efficiency model from Monteith. Essentially, it's representing plants' ability to convert solar radiation into biomass. And it turns out that the amount of absorbed solar radiation is directly related to satellite-based vegetation indices like the Normalized Difference Vegetation Index. And so NDVI is a really important input into this model. And the conversion of solar energy into biomass can be then modified using temperature and moisture constraints. So there are some kind of physical bounds on how this model behaves. Now, because this model is representing plant conversion of solar radiation into biomass, that looks very different for different types of plants, probably at the level of species or individuals, but certainly at the level of plant functional types. So one challenge in applying this model historically has been, well, how do we represent the predominance of different vegetation types on the ground? You'll see in this, this kind of shows that for each vegetation type, there are different parameters in terms of light use efficiency, temperature influence, moisture constraints, respiration. So those are empirically derived parameters, but we still have to represent the vegetation types to actually feed into this model. When we look at the landscape, this is a landscape in Wyoming. This is a very heterogeneous landscape. It's really diverse. We see, it's forested in the southern portion of the landscape, grading into maybe mixed shrubland and grassland, grading into a more herbaceous kind of shrubland in the northern part of the system. Well, previous versions of this model used categorical data to represent the plant distributions on the ground. So you can see in this map, forested areas, shrub-scrub areas, and herbaceous areas. And so those areas have kind of constant biomass, and it's difficult to draw inference about what's happening with any vegetation type on its own. The wrap cover is meant to solve for this problem by representing the predominance of different vegetation types. So you can get, well, for one, you can get estimates of production from annuals and perennials for any location. And then for two, this is representing not each pixel just as a discrete class, but actually the kind of relative dominance of each of the vegetation types. So that makes the wrap really dynamic when there are changes like wildfire and other types of disturbance. And so I think that's just useful context to understand as you're interpreting these data. With that, for any additional detail, I would refer you to the publications. There's a really nice and readable publication from Matt Jones that I referenced on one of the previous slides that, you know, I think will give you a better understanding of this data set. So if you're interested, I would refer you there. From here on out, we're going to talk about applying these data. So our newest reports that we have available are our vegetation production reports. We've just rolled these out in the last few months, so we didn't have these when we gave our Climate Engine Basics training back in June. So I want to walk through these in a little bit more detail. Similar to with our drought reports, we have a step-by-step tutorial article that's linked here on this slide. You'll have access to these slides after the training. We link to this specific report, which you can open up, and then we have a detailed video tutorial. So this slide is here for your reference, but I'm going to open up this, this report in our reporting page. So when I click that link, it'll open up the Warm Springs Creek allotment, which is in the Missoula field office. You'll see we, like all our other reports, have these for every state office, district office, field office, and grazing allotment. You'll find more detail on how to interpret these reports in our tutorial video, but I do want to walk through them here. In this first panel here on the left, we have two types of maps for each of our two vegetation types, annuals and perennials. The top two maps are maps of year-to-date production. So it's summing up all of the production that's happened within the calendar year since January 1st and putting that on a map. And we can see, especially with the perennials, really distinct patterns in terms of where the perennial production is highest. Importantly, as you look at the map of annuals, there's not a whole lot of production from annuals in this particular grazing allotment. And so this next set of maps is an anomaly relative to a longer term period. So this is comparing year-to-date production for the current year, 2025, to a 20-year average from 2005 to 2024. So what we can see in the perennials map is that this unit is pretty well below average in most locations spatially, but that there are some important kind of differences on the landscape as well. As you look at the map of annuals, you'll notice that this is a really colorful map. And what's happening here is that, well, first off, this map in this case isn't going to be very useful to you. And the reason is we talked about annuals being not very productive in this system. So by the time you get to an anomaly map like this, it's the percent of average. So we're dividing the year-to-date production by the average. So you end up dividing small numbers by small numbers, and you just get this really kind of not very useful map. We would encourage you, when production is low for a vegetation type, not to try to draw too many conclusions from a map like this. It's going to be these maps are going to be most useful for providing context with areas that have some significant amount of production for that vegetation type. Below the maps, we have this heat map. And so in this figure, and I'll zoom in on my screen a little bit so you can see a little bit better. Each row is a year of data, and each cell is one 16-day period. So I mentioned these are 16 data available every 16 days. What we can use these figures for is to see, are there changes in the timing of production? Or is this unit really variable from year to year? Is there some sort of trend in the production data that's seasonal. So you can kind of at a glance see here that this allotment was mapped as being much more productive from maybe 2005 through 2015. And then it's been less productive since then. So you might be interested in investigating more. Was that something related to climate or some sort of other disturbance that might have occurred? So this can provide a lot of information at a quick glance. This table will provide a number of different statistics in terms of annuals, perennials, total production, and precipitation. So in the left-hand column, we have the year-to-date production and precipitation. In the second column, it's the average year-to-date production and precipitation. The next column is just the first column divided by the second column to get the year-to-date percent of average for production and precipitation. Next, we have the trend in production over the period of record. So we can see pretty strong negative trends in perennial forbs and grasses. And then the last column is average production over the total year. So kind of, what would you expect to have at the end of the year on average over this unit in terms of production and precipitation? The next figure is showing the average rate of production over this year compared to the historical distribution. So here we can see that this in 2025, production started off below average. And then starting in about mid-June, it actually dropped below all of these kind of area plots, showing that this was the least productive year on record over the past compared to the last 20 years. So that's a pretty significant finding. The next figure is the same data, but we're accumulating it through time. So you can use this to kind of see, okay, over the entire year, are we above or below average, kind of putting aside timing. And we can see that for annuals, we're well above average. And we see that in the anomaly figure here on the anomaly map on the left. And for perennials, we're well below average. The shading here is the interquartile range. So we're really well below average across this unit. And that also relates back to this anomaly map. And then finally, we can see the precipitation summary. And what we see here is that precipitation mostly shut off in kind of late May and started to trend pretty well below average. And that's when we started to see production really shut off for this region. So that's a pretty significant finding. The last thing that I want to show you here is similar to how Kristen showed the feature summaries for climate. We can do the same thing with the production data. So if we go into the Climate Engine app, you can again here as the visualization layer select feature summaries. And now instead of selecting climate, we're going to select remote sensing. And I'm going to select the wrap yearly production data. And we have a bunch of pre-calculated layers available. So you can compare the current year to longer-term averages. You can map trends. I'm going to map the period of record trend for this area, or period of record trend over all the grazing allotments in the BLM. Our color ramp isn't particularly useful. So if you end up with a color ramp that doesn't look very kind of, if you want to modify the colors, you can do it under this computed map drop down. And so I'm going to click compute map with some different colors here. I'm going to try that again. Oops. And now we get a map of production anomalies for 2024. Or no, sorry. Yeah, this should be 2024. Sorry. Trends in production from 1986 to 2024. So you can use this as kind of a targeting tool. You can drill in through the reporting website, but here you can say, within my field office, I'm seeing, this particular allotment that is trending quite negative. Let's go investigate that. I'm going to go open up the production report and see what this looks like. And I can see in the heat map that, this area seems to be much less productive than it was before. I can open up the site characterization report and see that perennial forb and grass production appears to be trending negatively through time, and look at the cover summaries as well. So we really envision, you being able to use this to kind of target the areas you're interested in spatially, and then use the reports to really kind of deep dive on what might be playing out in the data. So that's what I have for this section. And I think we can, I'll kick it back to Tim, and we can open things up for any questions that folks might have before we transition to our BLM presenter.
Hey, thanks a lot, Eric. I appreciate that. I'm actually curious. Feel free to shoot any questions out, but I'm curious if we could get a show of hands, or not a show of hands. Let's do a show of hands. If you've had a chance to look at the site productivity reports before. I know these are, as Eric mentioned, these are quite new. Okay. Yeah, pretty small number. Okay, thanks. Also, I'm assuming the inverse of that, folks haven't seen these yet. If there are any questions, certainly let us know. Furthermore, when you do get a chance to look at these, please let us know if you've got some questions that come up, whether it's questions related to interpreting what's being shown on the report, or questions about the underlying product. I see we've got a question from Charlotte. Are the production estimates influenced by grazing throughout the season? The short answer is yes, because it's a dynamic-based model, and the remote sensing is capturing some of that. That said, I hate to put anyone on the spot, but I do believe we have Sarah McCord with us. Sarah, if you would like to chime in at all, please do so.
Hey, yeah, Tim, I'll just echo, yes, the estimates will be influenced by grazing, in the sense that you will have maybe a different NDVI signature or greenness signature from that pixel if there's been grazing versus not. But there's no direct parameterization for grazing amount in those estimates. So it'll just be picking up whatever spectral signature may have occurred because of grazing or any other disturbance.
Thank you, Sarah. I appreciate that. Yeah, it's a great question, Charlotte. It's something that a number of people have been thinking about for a while, and in the remote sensing world, and trying to see what they can tease out. Keep in mind that these are baseball infields, and so that spectral response is an amalgamation of everything across that baseball infield. And so if you do have intense grazing pressure, we should see that reflected by a dip in NDVI. But it's not always a one-to-one correlation there. Yeah. Jacob, do you have a question, or is that a rogue hand I see? Okay, I'm not sure Jacob has a question. Yeah, it looks like we have a little bit of a side chat going here, which is great. Yeah, production, not standing biomass. Potentially, could it potentially be net production depending on the situation? I think so. Although, Sarah, if you want to add to that, please do so, or expound on that.
Yeah, I need to think about that. So any given production estimate for a 16-day period is whatever's produced for that period. So anything that was produced in the period before would not be represented in that map. And I don't know, Eric, if it's worth pulling up that graph again that kind of shows the accumulation curve. But any one individual pixel is just going to be like one little slice on that top current year production curve, and then when we can add it all up into a cumulative production.
Yeah. Thank you, Eric, for pulling that up, and thank you, Sarah, for the comments. I appreciate that. Okay, any other questions before we move on? Great question, Charlotte. Thanks for those. Okay, so next we've got one of the more popular features of our climate engine workshops has been having someone from a state or field office come on and give us a vignette or a series of vignettes of how they've been utilizing some of this information in their local area. And so we had Wyatt Faraday gave a great presentation a couple weeks ago in the riparian wetland, and Ken Holsinger wowed us last week with everything that he's been thinking about in the upland vegetation. And this week, I'm happy to welcome Nicole Hupp with us. Nicole is the Montana State AIM Coordinator, although currently she's acting as the National AIM Lead. And she's here to talk about how they have used some of this data in Montana. So with that, Nicole, please take it away.
Thanks, Tim. Thanks, y'all. So far, Eric and Kristen, I'm learning a lot with every one of these. Okay, I'm going to try to share my screen here. Oh, sorry, the computer is getting weird. How's that looking for the other presenters?
I think that looks just fine, Nicole.
You know, I'm going to try again. It's being weird on my side now.
Just for those of you that have never seen Nicole give a presentation, she always does this at the beginning to kind of like lower expectations, and then she comes around and just knocks it out of the park. So just building a little excitement here. Jess knows what I'm talking about. Thank you, Jess.
This works. I learned that my network cable doesn't work, so I'm on Wi-Fi at the field office today. So that's exciting. We'll see. It looks like my slides are still getting ready to share.
We do see them on our end, Nicole. I don't know.
Oh, you do?
Yeah. Yeah, we see challenges and
weird.
opportunities, which might be a fun or surprising situation.
That is surprising. Okay. Do you see the beginning now?
We do. Yeah,
okay,
now it's
cool.
on Remarkable.
That's great.
Yep.
Okay. Thank you. Okay, well, thanks y'all. I'm excited to share some more examples from my side of the world using Climate Engine tools, specifically looking at the productivity products that Eric was just sharing. And I wanted to kick things off by giving a shout out to some of the people across Montana Dakotas that use these tools formally and informally all the time. And they really benefit, I think, by working together as an informal community of practice. These are different project leads from across Montana and North Dakota and South Dakota and some of our state leads. And these are people who are implicitly asking themselves all the time, you know, how do I narrow down where I should go look in the field? And how can I overcome the general overwhelm of all the products available to me and data available to me and just start somewhere and kind of, how do I get curious? So these people have kind of worked together to become, you know, some degree of field level super users. And I want to acknowledge that it does take some level of bravery, skill to implement a new product and use something new. So I just really want to acknowledge that these people, I think, have benefited a lot by working together as a community of users. And so I think all this stuff is more fun if you bring along a buddy. So I want to encourage everybody out there to reach out to a super user or find somebody else with you as you go down this pathway of using some of these products. And I view most things through the lens of the assessment, inventory, and monitoring data set because I'm the state lead for Montana Dakota's AIM. And so the first place I look when I'm trying to find data or explore something is the AIM data set. It's really robust. We've got nationwide tens of thousands of points, sample locations. And in Montana, Dakotas, we've got, over 5,000. That's a lot of points. It's super useful. And it's still not, it's not everywhere. It's in a lot of places, but it's most powerful when we can link it up with remote sensing. And so we found that, in this example that the AIM data is really compelling. Here I'm showing the Pryor Mountain Wild Horse Range, which is in south central Montana. And in the Pryors, we just have a really unique plant community there. The species are, there's many rare, sensitive, and endemic plants there. And so in addition to the fully random land use planning sample selection there, the project lead, Jason Sprung, has made sure that we collect additional AIM points intensively in this mountain range so that we can have a little bit more decision-making space. And so we've used AIM data here in the Pryors alongside the rangeline analysis platform. We've used some of the earlier versions of the drought tools and the drought monitor all together to try to understand some trends in the plant community over time. Oh, wow, this is not the most smooth. It's a little buggy on my side. So we've brought together the AIM data sets with other products to provide a clearer picture of this location, and then we've used those as informative pieces in the land health evaluations and use those as appendices in environmental assessments. So if anyone's curious about this specific example in the Pryors, you can find it on ePlanning. It utilizes some drought products and AIM data, and I would love to talk with anyone about that who is curious. And we've had other great examples shared by Ken last week, and we've got habitat conditions assessments and land health evaluations and environmental assessments, and some of those I've shared, as well as from Montana Dakotas. We've got examples from Heather Nenninger and Rachel Miller and Jess McDermott. And I'm gonna do something a little different today, and instead of describing those again to you, I'm going to talk a little bit about how we can get a little more curious in using these products in the informal side of things, and what happens before we create the formal products. How do we just start asking questions? How do we start getting curious and use things like Climate Engine for fieldwork planning and exploratory data analysis and just getting a conversation started? And I think we've all been there before when someone comes up to you with a figure about your favorite polygon. It's really hard to not be like, what's going on there? What does this map do? What is that? What does this line show? And I find that to be really fun. I think it's the most fun part of my job, is getting to put our heads together and think about, do these trends make sense to what you know on the ground, and using that as a conversation starter. So that's a little bit of what I want to share today. Sorry, there's quite a lag. And that curiosity is particularly fun to use these tools in the places where we don't have AIM data everywhere. And it's not shocking to anyone here, but we do not, nor will we ever, have wall-to-wall ground-based data for every single BLM allotment in every single field office. And so in those cases where you're trying to make a decision for an allotment or in a polygon where we just don't have any other ground-based data, I think starting with the remote sensing tools is a really great place to think about what you need to know. And sometimes you might find, we need ground-based data here. Or, who knows what you might find, but I think these are great opportunities to look to remote sensing offerings. And this is a picture of Missoula Field Office with a few examples of some allotments that have not a high density of AIM monitoring. Some of these have, a few loadic points in the green polygons. Some have a terrestrial point for the most part. They're lacking points, which is kind of ironic because I am the state monitoring coordinator for Montana, and I am based here in Missoula. And I look around sometimes trying to help them use their AIM data, and I feel badly that I have given them poor customer service in not giving them more AIM data to look at. But part of the reason they don't have a ton of AIM data here, because, and this one example of Douglas Creek in particular is what I'll be focusing on today. You can see it has one loadic point. Part of the reason there's not a ton of AIM data here is because there's a lot of trees here. This field office has mostly forested ecosystems. As you can see here, logging is logging operations and forest management is a big piece of what Missoula Field Office really focuses on. And so there isn't a high density of AIM data, but we do have other remote sensing tools that could be useful here. And so I was kind of poking around the field office here, and I always do over the years, trying to be like, how can I help you? How can I help you think about how to use the range analysis platform or some of these tools? You know, what can I do for you? And I'm always looking for ideas on how we can use these tools in this specific field office. Sorry, I swear that my transitions are usually smoother than this. So working with Missoula Field Office, I asked them, you know, does anybody have a few polygons they're particularly interested in that I can help you think about how to use some of these tools? So we started poking at Douglas Creek, and I just, using the tools that Eric just showed, I clicked on all the buttons. I want to see a report of each one of these for Douglas Creek here in Missoula Field Office. Obviously, my typical pathway to teaching people is to do it here in Teams. So this time I tried a different route. I just printed them all off, took my pen and started walking around the field office, talking to the people who I knew who would be most interested in this, and tried to see what we could do together, you know, using that curiosity to ask questions and maybe generating some trust in these products or not. Just let me know if my slides are not syncing up with what I'm saying. So the first thing I took around that we looked at was production. And like many of you, this office used to have a lot more range staff than it does right now. So I assumed the production estimates would probably be pretty useful and compelling for this office that doesn't have a specific range person to really think about these things. So we started with the production product that Eric just showed. And I'm just going to hone in on that current year production rate compared with historical percentiles. And so, you know, with time on the X throughout the year and total production on the Y, this looks pretty similar to the polygon that Eric looked at. Production was quite low for Douglas Creek in Missoula last year, like lower than some of the lowest, which was not surprising. The Blackfoot River was super low. It was a super droughty year in Western Montana. So that kind of passes the vibe check for us and when we look at production by the different functional groups, we see that annual forb and grass cover was much higher last year than what we would typically, you know, than what we have seen over time. Similarly, perennial forb cover was a whole lot lower than what we expect out of average. It took us a while when we were looking at this one in the field office to appreciate that the scale bars are really different here. Perennial forb cover here was around, forb and grass cover was around 600 pounds per acre. Annual forb and grass was 40. So it's more than double what was historically there. But that's comparing 20 pounds per acre to 40 pounds per acre. But we also see really low precipitation throughout the year, which all of that really tracks. And so I took this over to Jen McNew, who has a botany background, and we were talking about the perennial and annual cover. And then as we got more curious and we got more loud, we started talking over the cubicle to Mitch for work, and he was coming over. We were looking at it all together, going over the map. We started kind of poking around at it. All of this kind of tracks with their knowledge of this specific allotment. So after we looked at the production report, we went on to look at the site characterization product. This is where the story gets more interesting. First of all, looking at this allotment, we could see, I'm honing in on this, that tree cover, there's some trends in where we see tree cover and perennial forb and grass cover, particularly. Most of the allotment is forested, and some of it has pretty dense perennial forb and grass cover over time. So, okay, that makes sense. This is a forested area. The grassier parts are over here. That's making us think, okay, if I was a cow, I'm going to be spending a lot of my time in this part of the grazing allotment, less time up there, like starting to wrap our heads around what might be working on the ground here. Just building some more curiosity and building some trust in the product. And again, we honed in on trends in Perennial foreign grass cover, which we saw was declining over time, but what the earlier production estimates didn't show, obviously, is trees. And in this particular allotment, we saw a pretty strong increase in tree cover over time. So this is percent cover on the Y. We've got time on the X since 1986, which is when I ran the model since the beginning, since the dawn of time when Landsat launched in 1986 to present. Tree cover has been on a pretty steady incline, with a pretty inverse relationship with perennial foreign grass cover. In the US, that would make us think forest encroachment to see tree cover to that degree. However, this is already a forested plot. There are trees here. There's supposed to be trees here. This particular area that we were looking at is supposed to be forested. So I moved on from the botany cubicles over to the forester cubicles to go talk to Jody Wetstein, because she's a forester, and I snagged another forester in the break room to try to understand more about the trends in tree cover in this polygon over time. And yes, I learned a lot, and some of it I already knew, mostly that commercial logging has occurred in most BLM lands in the Missoula Field Office for 100 years. Most of the land that comprises this field office was owned by Plum Creek Timber Company and was purchased by Nature Conservancy before coming into BLM lands. And so that is part of the story here of what happened before 1986. And that really got the wheels turning for this office in terms of, okay, as I think about this allotment, it's starting to ask some questions about the history of the space and what were the foundations that led to this snapshot in time. And where we kind of have left it and where the conversation will continue to go is, are these questions that were generated by the figures. Was this area burned recently? When did the commercial logging start here, and when did it end? What does the grazing permit look like? Is there still, have there been trends in that over time? Also, some bigger questions that are out of my element, which is forest succession here. Was this once logged, and when those activities ended, has the forest just filled in really densely? And we're just in a later stage forest succession process here? Is there some relationship between the forest succession and drought? And at the end of the day, what community is supposed to be here? And all of this is really helpful as this office has to review their grazing allotments without having their previous, range person who did that. And so they have an opportunity to look back on how they've reviewed grazing allotments in the past, and also look ahead and think about how they want to do it in the future. And now's a good time to start poking around at our remote sensing tools and see how useful they might be in streamlining some of these processes. And at the end of the day, we really honed in a little more closely looking at the relationship. This is also generated from Climate Engine with time here on the X, perennial forb and grass cover on this Y, tree cover on the other Y. Note that I had to set the axes to match. It didn't default to that, so buyer beware. Wasn't hard to fix. And we just kind of looked together to appreciate that tree cover and perennial forb and grass cover have done quite a dance over the years, but it looks like trends are pointing more towards the direction of that relationship flip-flopping and the forest canopy closing off a little bit more, providing less perennial forb and grass cover. So this has been something interesting for the field office to consider, and we're not sure what the next steps are. This is just an example of how you can use these Climate Engine tools to be a springboard to take a closer look. Because to me, when I look at this, I'm like, I just want to go out to this allotment and kind of look around. I believe what I see based on what I know from Missoula Field Office. But this is a compelling way to start thinking about this, especially in an office that thinks a lot about fuels treatments and drought. And we saw extreme drought in Missoula Field Office last year. And as they think about forestry and fuels operations here, they're thinking about what drought might look like in Missoula Field Office going forward. So as we looked at the drought reports for Missoula Field Office, we didn't really get much of a chance to poke around in this, but it does look like for this allotment and for most of the field office, they were experiencing some degree of drought last year and in previous years, and the long-term time series comports with everything that we've seen on the ground. So all of that, I think, could be really useful for the field office if they wanted to incorporate this even as an appendix for a land health evaluation. This office does environmental assessments at the watershed scale. These could be super quick and easy appendices to include in those types of analyses. I want to acknowledge, I wanted to share this example of exploratory data analysis from the start because all of the finished products that we share, remove those initial pieces of deciding what areas am I looking at and what ought to be included in my report writing and in the questions that I'm asking. And so I wanted to share this with others that hopefully you can find these tools be useful to just start poking around and thinking about how you want to inform your decision making in your own field offices. And in this case, if we found something that was super compelling, maybe they're like, you know what, Nicole, can we get some aim points in this specific allotment or in this part of the field office where we're seeing these really strong trends? Can we create an assessment, inventory, and monitoring intensification process or project to get more data in these areas? So with that, I just want to share that the general challenges for using these tools and utilizing data in our decision-making process is we always need more examples. Looking at someone else's example is just super empowering. It's nice to follow along with what someone else did. So I just want to encourage anyone that as you get going in this process to use these, I hope you share your examples, even if it's just within your own community or with your AIM leads or whoever else in your state, because we want to see what you're working on and help you or champion your efforts. I swear we won't just like put you on blast. And that we always need more data application support. And I think we have a handful of data analysts in the state, and I know they're working double duty right now, and those folks can be super useful as you start to get your feet wet in using some of these tools. So with that, I'll wrap it up. Are there any questions for me before I hand the reins back over?
Thank you, Nicole. As we're waiting, if there's any questions, I really appreciate the information, and it's really interesting that you can use this information to help gain an appreciation for land use legacies in your area. Really nice to see that. And one other little nugget, you also showed a slide that had two different plant functional types. You can look at how they co-vary. That's really powerful to be able to do that. Also for folks that use the fractional veg cover a lot, the RAP or the RC map, it's really nice to be able to look and see what those products may look like in terms of similar plant functional types with each other in the same way using a graph like this. But as Nicole pointed out, be sure to set your axes to the same scale, because that'd be very helpful. And finally, when it comes to bigger picture application, a lot of this stuff is fairly new, particularly with respect to how it may be used in decisions within our agency. And so to Nicole's point, yeah, examples are so helpful because they equal blueprints or a starting point for a blueprint for so many other folks. So if anybody has some of those, please ping us and let us know. We'd love to share them and try and learn along with you all with what you're learning. Robert has a question here. Has there been any analyses? This is not specific to Nicole, but has there been any analysis of how accurate production values in RAP are compared to the field? I'm again going to turn that over to Sarah McCord, but I believe we also have Ken Holsinger on here. I know there's some limitations to why we can't do that at broad scales, but I think Sarah and or Ken, if they don't mind me putting them on the spot, might want to comment very briefly.
I can go. We did some field work on an allotment that we had some real tough land health issues on. A whole lot of plot level collection. I'll pop in the chat. We put a sort of case study in the RAP bibliography. I'll share with you guys. You're welcome to read it. But really fascinating similarity. Conversely, we also collect a lot of production data on other land health plots that we do. And interestingly, we're seeing pretty good agreement. Seems like things that are in our higher elevation, more productive landscapes are a little off, but down in our drier landscapes, it's kind of scary how good it is. So I'll pop that paper in. You guys are welcome to look at it. And any questions, feel free to reach out.
Thanks a lot, Ken. I should have remembered about that case study, but yeah, that'd be really helpful if you don't mind sharing that. That'd be great.
Robert, that question, has come up a lot across our state, and Ryder Renz, our state range lead, and I have looked at that together. And yeah, I would encourage folks to poke around and look at it compared with if they have any known values in their state. Because I think, in my experience, whenever we've kind of tested it against what we know on the ground, it's only built trust in the estimates, but I don't want to sound too overconfident.
Thanks all, and appreciate the question, Robert. And Eric's got a nice link in there as well to comparing it with some NRCS, NRI data. But with that, I'm going to turn it back over to Eric for our final stretch here. And thanks for staying with us all.
Fantastic. Let me adjust my camera here. All right, I think we're back. Oh, it's going to try to find me wherever I go. Great. Well, yeah, that was a great presentation. Thank you, Nicole. Yeah, I agree that last point about finding examples. I think, we're seeing more and more people start to adopt these data sets. It's just really helpful and instructive to understand kind of, what some of the needs are. And for us, as we're developing tools too, to understand how people want to use these data. So I really value, having some, I think as a community, tool developers and researchers working with resource managers and understanding each other's needs. So with that, I'm going to jump into our last example here. All right, we'll go into presenter view. This last demo is going to bring a few things together. Nicole highlighted some allotments where forestry is very much a part of managing that landscape. We're going to be, in this example, highlighting areas where complex histories of pinyon juniper have played out. And so there's expansion and densification, and also primary forests that have existed as well in some of the adjacent lands, and that's in eastern Nevada. And what we're going to try to do is use the RAP production data to assess the vegetation response after treatment. And to do this, we're going to look at a large kind of watershed scale restoration project, the South Steptoe Valley project, which is just southeast of Ely, Nevada. This project was meant to improve habitat for sage grouse and reduce risks of increasing fuels contributing to catastrophic wildfires. The treatments were implemented between 2013 and 2021. And you can see the effects of the treatment quite visibly in satellite data. So it's an interesting kind of case study. Now, these types of treatments have risks associated with them. After trees are removed, that can create an opening for invasion by invasive annual grasses. And then additionally, the public can have negative opinions about projects like this if they don't understand kind of the habitat improvements, or just seeing these very large kind of treatments, cutting trees. And so for these reasons, we want to focus on being able to demonstrate outcomes, and communicating some of the outcomes we feel like is important. And we're going to highlight a couple ways to do that here. I've pulled out some of the things I'll show in the app into these slides. So these are here for your reference. But I am just going to jump into the app now to get started. So jumping into the app, I'm going to zoom in on our region here. So I'm going to find Ely, and it's this area kind of south of Ely, the Steptoe Valley And we can see the effects of the treatment just in the Google Maps imagery here to begin with. Now, a couple things have changed in Climate Engine since our Climate Engine Basics training. If you attended our last two trainings, you would have seen this. But I just want to highlight that we now have these raster overlays, so you can bring in layers like Surface Management Agency to look at who owns particular pieces of land, or the National Land Cover Database to look at land cover patterns. And so I just mentioned that you can put these data to work in a few different ways that we won't highlight. So if you're interested in that, look at a couple of our previous recordings. The other thing I want to highlight here is we now have high resolution base maps. So we can turn on this historical imagery layer, which is tens of thousands of historical satellite images over the continental US. I'm sorry, over the Western continental US. And we can see imagery here from, I think this is 1954 for this particular region. And so this becomes a useful contextual layer as we're looking at then higher resolution NAPE imagery, which is another layer we have available. It'll tell you what years are available for a given area. So I can look at 2006 and see the extent of tree cover over this area. If I want to then look at what is another good year, 2015. Treatments haven't started in this area yet. I think by the time I get to 2017, we start to see some of the effects of some of those treatments. And by 2022, the treatments are, you can see the treatments at a landscape scale. So, all right. I think I was thinking about whether I would skip a step. I think I'll keep that step in, but I am going to turn off this layer. So that's valuable context. One thing you can do in Climate Engine quite easily is create trends in data sets like RAP or RCMap. And so I do want to look at how the history of tree cover and the effects of the treatment show up in those products. So to do that, I'm going to select remote sensing as the data type and scroll down in our, again, long list of data sets to RAP cover. Again, you can use whichever data sets are useful to you. I'm interested in tree cover here initially, and I just want to create a trend map over the period of record prior to this treatment. So I'm going to select 1986 to 2010 as my period I'm interested in. And we get a map back that shows largely increasing tree cover, but some interesting patterns of, this was an earlier treatment. We can see perhaps some mortality or wildfire events happening, but and then at the toe slopes is where we see quite a bit of increasing tree cover showing up here. So that may be an indication of kind of expansion of tree cover in those areas over that period. If we move this range forward to the last 20 years, kind of centering on the periods in which the treatments were applied, we really clearly see the effects of those treatments on the landscape. So this is a useful way to quantify those effects of those treatments. But for this example, I want to take things a step further and look at one particular treatment from 2016 and see what we can look at in terms of the production data and the vegetation production response. So we're going to analyze one particular treatment. To do that, we'll use the Make Graph tab. And I'm going to show you how to upload a shapefile. So let me pull up my shapefile. I've got this. Of course, I'm in the wrong folder. Now publicly navigating to, okay. And I'm going to add this shapefile, which has a bunch of treatments across this region. And you can just click on the polygon you're interested in. And I'm going to use this polygon as my kind of area of analysis here. the first thing I am going to do is just pull production data from RAP over this area for total production. So I'm going to select RAP production and set my time period to the whole period of record. And now we're ready to pull the data. And so we can really clearly see the vegetation response following this treatment here. Now, and this shows up in 2015 to 2016. So now what I'm going to do next is we want to investigate annuals versus perennials and the kind of the dominance of those two vegetation types. So here I am going to create a 2-variable plot, kind of like Tim was describing earlier. And I'll select annuals as my variable 1. And for variable 2, I'm going to select, again, from RAP production, perennials. Time periods are matched up. And I'll click compute time series. And when we get the figure back, we'll see that both perennials and annuals spiked following this treatment. Now, what you'll notice here is that we have a mismatch, like Tim was describing before, in our y-axis. So you can modify your, like by default, it's just going to stretch the y-axis to the limits of whatever data come back for your variable over that period. So if I set this to 350, then these will be on comparable y-axes, and we can see that there has been a response from annuals, but the response from perennials is much more significant across this land unit. And so the last thing that I want to show is how we can kind of quantify. I mean, I think just to back up, I think this already is telling a pretty useful story. We're seeing that perennials are far more dominant on this site after this treatment, and any kind of invasion by annuals should be monitored, but is probably limited over this particular area. The last thing that I want to show here is how we can kind of better quantify the response from perennials while accounting for climate. And to do that, I'm going to bring in climate. So this, we're going to use a summary time series and select GridMet as our data set, just like Kristen showed before. And here we're going to sum up precipitation over the water year to do a comparison between precipitation and production from RAP. And so it's these types of assessments you can do to kind of characterize how production is responding to precipitation in any given year. And in this particular site, you know, the driving influence is from this particular treatment. And so we do see some, you know, especially in the post period following treatment, production appears to be responding to precipitation to some extent. Those wetter years are also greener. But the treatment effect is the driving factor. So to quantify that treatment effect, we can use the kind of last figure I'll show here, which is this 2-variable scatter plot, where we're relating production back to precipitation directly. So precipitation will be on the y-axis, precipitation will be on the x-axis, production will be on the y-axis. And I'm going to separate out the pre-restoration period from the post-restoration period. And I know I'm going a little bit fast through this and skipping a little bit of explanation because we are very close to the end of our time here together. So what you end up with is this figure, and what this figure is effectively showing, if you attended the riparian and wetland training, you'll recognize that from this session, from that session. But what you can see in this figure is that while accounting for precipitation, we're seeing much more production in the post-restoration period. The other thing that you can see, and it'll be a little bit clearer if I move this legend around, is that the vegetation appears to be responding more in the post-restoration period than the pre-restoration period when there's more precipitation. So those wettest years are also the most productive years. And so that is the end of this last demo. Like I said, the slides will have more information. I don't have links to each of these figures because by the time you bring in a complicated shapefile like that, our system doesn't like that. So I added figures and you'll have the recording available going forward.
Hey, thank you very much, Eric. I appreciate it. I know we got a little off base with some of the questions, which were fantastic. We do have a couple of minutes here. If anyone has any questions or comments, before we get into some of the survey stuff, and if you're thinking about some questions, I might just throw out something that I mentioned early on, that this application is a bit like exploratory data analysis on steroids. And you know, I'm a big fan of the 2 time period scatter plot that Eric just showed. To be able to do that and you know, very quickly look at how your y-intercept may have shifted up or down pre or post treatment or event is incredibly powerful. And I just can't stress enough all the data that goes into that. To be able to generate that is really, really cool and really, really impressive. So I'd highly encourage everyone to, you know, think about doing that in your area of interest, and in hopes of getting a better hold on things. So yeah, before I turn it back over to Eric, any questions that we might have on that last segment or anything we covered today? I know we've thrown an enormous amount of information at you all, so I wouldn't be shocked if it was still steeping for most of us. Okay, well, with that, Eric, I'm going to turn it back to you for the closing slides and thoughts. Thank you all.
Awesome. Yeah, and all right, so yeah, as we move towards the end here, did want to just compile and share some resources as you're getting started using Climate Engine or taking your next steps if you've been using Climate Engine for some time. So you can find much more information at our website. We showed the reporting site earlier in the demo as well, so we have the link to that. And then our support site has a lot more information on the data sets that we highlighted, different demonstrations. So if you want to dive in, there are a bunch of different examples, some of which have videos. And then you can follow us on the socials as well. So we have a YouTube channel where we post tutorial videos, and so subscribing is a great way to see those videos as they come out. We've started a Substack to publish longer blog articles, and we're active on LinkedIn with announcements about new data sets and things like that. To Nicole's point about collecting examples, if you are using Climate Engine and you're able to share an example, we do have a form for trying to compile some of those. As we wrap, we do have this survey, and Kristen and I both look at this survey pretty often and really try to think about the results, you know, how to kind of build on, you know, the results of this survey. So if you have feedback, we would love to hear it, and we'll take it very seriously as we plan future sessions. As you're starting to digest this information, a great option is joining Tim's office hours tomorrow. I think you all got an invite earlier today, so encourage you to join that. The link is available here as well. And with that, this is our last session. I just really want to thank everyone for joining. We haven't gotten to do this for a while because we missed being able to do it in October with the lapse in funding. And it's always really fun to get in front of groups like this and see how people are interacting with the material. So I know it's a little bit harder online. We'd really love to do more of these sessions in person. And hopefully we'll have some more opportunities going forward. But if you have questions, we'd love to hear from you. And yeah, just really thank you for your attention. And yeah, keep an eye out for the link to the recording after this, and we'll try to not be strangers as well. I'm going to put the link to the slides. Maybe Kristen already got them in the chat as well. So lots of links, lots of links in the chat.
We
Cool.
don't skimp. This group doesn't skimp on information. So the more the merrier. But hey, thank you all, and thank you for those that have attended the prior seminars. And again, as Eric mentioned, look forward to those slides. On behalf of the BLM and our colleagues at Climate Engine and our guest presenter, Nicole Hupp today, thank you all. Really appreciate it. And we'll be in touch. Have a great rest of the day.